So the next type of mathematical transformation, feature engineering that I want to talk about next is using the apply math. Right here. Apply math transformation to correct skewness, and then also for nonlinear relationships. So to correct skewness, the issue here is that when a feature is not normally distributed, then we get more error in our predictions, and we're not as accurate in our predictions for all values of x or of the feature. So what we want to do is, we have a couple options. Now, this isn't the modeling phase, so I don't want to go into detail on this yet, but there are other algorithms we can use besides multiple linear regression, which depends on having normally distributed features. So some data scientists will simply tell you, hey, don't worry about skewness, ignore it. Let's just go and pick decision trees or some other type of algorithm that doesn't depend on having normal distributions. However, in my experience, I've been able to get better model fit and accuracy sometimes, not all the time, but if I can correct skewness, I can often get better accuracy by using a simple multiple linear regression than some of the newer, more advanced algorithms that don't depend on this. So I like to go ahead and correct skewness as much as possible, and then it gives me more options down the road in the modeling phase. So it depends on what our skewness problem is. Is it a positive skew, which, as a reminder, that means that we get the long tail to the right. It means it's right skewed. Or is it a negative skew with a long tail to the left? Positive skews are much more common. For example, let's say we're referring to customers. We've got their age. Most of our customers are going to be younger with very few, and when I say younger, I mean starting at 18 or above, and there'll be very few who are in their 70s, 80s, 90s. So that's a positive skew. Negative skews happen. They're not as common, but one example would be ratings, movie ratings. Let's say I've got a data set full of movie ratings from moviegoers, and the average, let's say the scale is 1 to 5. Most people go to movies they like or that they think they're going to like, and so the average rating's not a 3, which is halfway between 1 and 5. Most ratings actually average more like 3.5 or 4 stars overall. There's usually fewer 1 and 2 star movies and a lot more 4 and 3, 4, 5. So that would be a negative skew, and we would use the opposite sort of corrections. So there's different ways to adjust for that. We've got more, mild or softer, more moderate, and more extreme corrections for both positive and negative. The idea here, again, is to get a curve to be more bell-shaped. So let me pull up a quick diagram here. All right, let's say that our histogram looks like this one right here. And we have some sort of right skew. What we want is some sort of mathematical transformation that will shift values here on the lower end to be higher values, so that we'll have fewer values over here on the left, more in the middle, and not quite so long of a tail on the right, and it'll look more normal. Well, if our distribution's like these, we have lots of these small values, what we could do is use a square root transformation. So think of what that would do for a moment. It might be easier to look at this in Excel. Let me pull up a new Excel window here and bring it down. Let's see here. Sorry about this. Making you wait while I adjust. All right. All right, so let's come up with a skewed distribution. Something like we have a 1, 2, 2, 3, 3, 3, 3, 3. All right, put in a few more numbers here. Let's do a few 4s, and then 5, 5, 6, 7, 8, 9, 10, 11. Oops. Okay, let me plot that in a histogram real quick. Insert, here we go, histogram. All right, so here's our right skew. Now, if we take the square root of each of those, let me show you what this is going to look like. Square root equals square root of that. And let's copy that down. I'll move this over here. Let's now take this one, insert chart. There we go. Okay, look at what's happened now. So the square root of 2, rather than, so the square root of 1 is 1, but when we shift to 2, the square root of 2 is not 2, it's 1.4, and the square root of 3 is not above 2, it's only 1.73. 4 is 2. So see how it brings 2 down by 0.6. Actually, here's a good way to look at this. Diff equals this minus that. And I'm going to paste that down. Look at how the adjustments get more and more extreme the higher the number goes. So right here, at the beginning, our adjustments are only 0.58. But the next digit, the adjustment's bigger. It's 1.26, then it's bigger and bigger. And as we go, the adjustments get continually larger. So what that does, it has this effect of taking some of these smaller values and pushing them over to the right. And see how this looks, it's not perfectly normal, but it's more normal than what the original was. So I'm going to call this our original data. This is our square root. Let me show you what a cube root does then. It's simply more extreme than the square root. Actually, I want to put that over here, I think. All right, so this equals, is there a cube root function? No, so what we'll do is we'll take this value and we'll raise it, there we go, to the 1/3, which is the same thing. All right, paste that down. So I'm going to hide this difference field now. Look at what the cube root does. The adjustments here are even more extreme. So going to a cube root of 2, the small number's a bit smaller, a bit smaller, a bit smaller, and it has this similar effect. So let's plot the cube root now. Insert cube root. Move it right there. Okay, this thing looks really similar to that one. Notice how all it did was adjust the scale a little bit of where it made the boxes. So my data here wasn't granular enough to really show you the difference between the square and the cube. But when you have more data with more granular differences among them, you'll see the cube root just pushes even a little bit further over to the right. All right, let me do one more here. Insert this one, and this one will be our ln transformation. This equals the natural log of this. Now you can actually use any logarithmic transformation. It doesn't have to be the natural log. It could be log base 2, log base 10. They all have the same distribution. They'll just adjust it to a different scale. Natural log has some other useful properties, and so we often just use that one as our default logarithmic transformation. So here, notice again, even more extreme, natural log of 2, 0.69, and so forth. Now, the natural log of 0 is undefined. So a common thing people will do is make their transformation the natural log of the value plus 1. Whoops, that is not what I meant to do. Natural log of f4 plus 1. There we go. Let me copy that down instead. Oh, yikes. That's better. All right, so now if we had any zeros in our data set, I've added 1 to everything, and so it barely increased these numbers, not by a lot. And that's okay as long as we use the same transformation for every piece of data. It's totally fine. So if you had negative 1s in your data set, this would be a problem though, because then it would turn those negative 1s into zeros, and you'd still have the same problem. So you can't do these transformations on on all values, negative values of x and 0. So anyway, let's plot this one's histogram, and let's see if maybe I chose numbers again that were too small. All right, I sure did. We're really not getting any more of a difference here, but that's okay. We'll go do it in Azure, and you'll see that the differences do get indeed more and more extreme, or adjust this distribution so that it looks more. Actually, it did change it a little bit more. See how this one's a bit higher than this one here compared to that? This one's a bit shorter, that one's a bit higher. Yeah, so it's pushing it a little bit more and more towards normal. And actually, one way you can see that is if we calculate skewness right down here for each of these distributions. Skew, let's go ahead and grab that one. Oh, that's square root. Let's do it over here for the original data. Oops, come on. Didn't mean that. Paste, paste. Okay, so here's our actual skewness score here. First one, it was too extreme. It was outside the bounds of -1 to 1. So we need to make an adjustment. We make a square root adjustment, and that gets it to 0.6. Now that's within the bounds that are acceptable, but we can get even closer to 0 with a cube root, and even closer with a natural log. Well, which one of those should you use? Well, there's some argument here. It depends on what the number represents. So in some cases, when theoretically there should be a natural distribution for this feature, a skewness adjustment is a great idea. And I would prefer the one closest to 0 over the raw data, although I would recommend keeping both the original and the one that's closest to 0, and send both of them into the modeling phase later on to see which one gives you a better accuracy. However, sometimes the distribution is meant to be skewed right from the beginning. Now, in that case, let me give you an example. Movie ratings. When I look on Fandango or whatever, and I am trying to pick a movie, and I see one movie that's 1 star out of 5, another movie that's 2 stars out of 5, and another movie that's 4, and one that's 4 out of half. So here's my movies here. Movie 1 through 4. Or I guess 5 now. This one is 1 out of 5. Oh, that's not what I want. 1 out of 5. 2 out of 5. This one's 4 out of 5. And then I got one that's 4.5 out of 5. Ignore that one. When I look at these movies and I see these two, a 1 and a 2 star, I do not care that this one is twice the star rating as this one. This one's a 1, this one's a 2. The difference between these of 1 is meaningless to me. They're both really low. I want nothing to do with either of those movies. Up here, though, I look at these. I see one that's 4 and this one that's 4.5. Well, I'm going to go with this one. That 0.5 difference has a big meaning to me because most movies hover around this 3 to 5 star range. And so a difference of 0.5 here is very meaningful, but down here a difference of 1 is meaningless. And so my actual preference function is skewed. I don't treat all values of x the same, and so there's not a normal distribution of movie ratings. In this case, I've often found that the original raw data is it's going to give me better fit metrics when I get to the modeling phase. That's why, and you don't always know if that's true or not, if the preference function truly is skewed, or if my sample was simply skewed and I just need to adjust it closer to 0. So I send the raw data on, and then I find the adjustment that gets me closest to 0, and I create that one and send that one along. And that's how I treat this. Now you might be looking at this and say, well, why would we ever use square root or cube root if this one's getting as closest to 0? That's because this won't always be the case. Depending on what the actual distribution is, this one could be 5. This one could be, this one could end up being 0.2. This one could end up being negative 0.1, and this one could be -3. And so in this case, I want to find the one that is closest to 0. So I'd say my cube root transformation is my best one. Now, you could even tweak it and go so far as to find the exact value that gets you right to a 0. Is it a 2.4 root or something like that? But that's going a little overboard. But I've done it anyway. Anyway, I hope this helped explain what it is exactly that we're looking for. So now let's do it in Azure. All right, I'm going to get rid of normalized data from the prior video, and I am going to apply math transformation, or sorry, operation. And let's move this in here. And in particular, let's find one that is skewed one way or another, and let's fix it. So let's go over here to sample skewness. Now, kurtosis, I may have mentioned this before in the book or elsewhere, kurtosis doesn't give us quite as much of a problem, really at all, in terms of machine learning or prediction as skewness does. So we don't really worry about adjusting kurtosis, even though a normal distribution likes to have something that's not too tall or not too flat. That's okay. We're going to ignore that and just worry about this one. So let's find a number. This one, that has some negative 999s in it. Let's ignore that. And right down here, 19, 17, 20, 45. So from right here, whatever this one is, let's adjust skewness on all those. Now notice they're all positive. Are any of them negative? Yep, here's negative, but it's close to 0, so it doesn't bother us. Whoops. In fact, there's more down here. So let's go ahead and just grab every numeric feature, and maybe we'll find some that we go too far on. So basic. Let's start with square root, right? And before I go any further, what columns do we want to do this on? Well, I've got it set currently to numeric all, but some of them we really don't care about, like ID. I'm not going to worry about loan status numeric either. I'll just keep the rest. That's fine for just example's sake. Now, last thing. This one's important because I always forget it, and I end up having to rerun my experiment every time I forget it. So output mode, what do we want? There's 3 options here. The default is result only. That's probably what yours is set to. I don't know why that's the default, because I've never once needed or wanted that output mode. What that means is it's going to give you only the transformed features and nothing else. Well, I'm building this data preparation pipeline here. I want to go through a bunch of different tasks, and I'm just going to daisy chain all of my features together, my edit metadata, my apply math operation. I know I've been doing them one at a time, but really we're just going to keep connecting the dots. And I want the data to flow from import data through each of those pills, and all the features I need should flow through all of them. So what I really want is either append or in place. In place means it'll take the original features and transform them however you've specified right here, but it will pass through anything else that wasn't transformed. So all of my categorical features will still go through, which I want to happen. Append is the one I usually prefer, because what that'll do is keep the original features, but it'll also append new columns for the transformed features so that you have both, and that's typically what I like to send along to the modeling phase. So let's run that. All right, let's take a look at the data that's come out of here. I'm looking at the data set, not the summarized data. Okay, let's look at these little histogram features here above. Look at loan amount and fund amount. Both have this minor right skew, not terrible. Let's go down to the transformed versions. All right, square root of loan amount and funded amount. Look how they're closer to normal and almost a little bit of left skew. Remember, it was barely above 1. It was like 1.1. And so just doing the square root transformation, we're probably negative now. Some of these other ones here, interest rate and installment. Remember how skewed those ones were? These look really normal now. Take a look back here. Interest rate and installment. See how these have these right tails? Yeah, those were positive skewed before, now they're much closer to normal. Well, let's go to summarize data and see what the actual skewness scores are. Let's move that down, and let's remember here all of our originals. Make sure I know what I'm looking at. Here we go, this column, skewness. So remember our 1, 2, 2, 19, 17, 20. Scroll down here to the adjusted versions. Let's find where those begin. Okay, right about here. It's kind of a pain, right, when I can't see it all at once. Oh well. Okay, I think this is it right there. Skewness, yep, let's go down to the 0.07. These ones, these were 2s before. Now they're really close to 0. this one, whoops. Our numbers here are all, these are looking a lot better, but some of them, like down here, these ones we still couldn't get. In fact, all the way through right below there, we couldn't get any of these down to within 1 to -1. Let's scroll over and see which ones those are. Total received late fees and recoveries. Yeah, those were the ones that had gigantic scores. So we haven't made things perfect, but it's a lot better than it used to be. So let's do this. Let's add another math operation, and let's see what happens with a cubed root and a natural log. So I'm going to pull these through, add some summarized datas, hit my number 0 so I can zoom out a little bit. Okay, so on this one, let's change square root to cube root, and I'll keep the same features. On this one, let's change, oops, not launch column, sorry about that. Let's change this to ln, but look what I got here. I've got natural log, but I've also got ln plus 1. I love that they've built that in just in case we have zeros in some of the data, which we do. So I'm going to use ln plus 1 so that we don't have that undefined problem. Okay, let's run it. Okay, even though this is still running, I want to take a look at those features and see if we've got them any closer to normally distributed histograms. So let's scroll over to that accounts delinquent. So let's look at the original. Right here. These are so skewed that we only get 1 bar on each of them. That's pretty bad. So let's go and let's find accounts now delinquent, the squared version. Right. Go a bit further. Oh, there it is. Still pretty bad on those two. Look, this one's starting to look better. Total current balance. This one's got one little tiny bar next to it. So these other two are still too bad, but this one we're getting a little bit better. Now let's take a look at the cube root version on those. All right, here we go. Looking a little bit better. Oh, am I looking at the wrong one? I am, yeah. Months since, all right. I think some of these features, oh, I've got too many, so it's not showing them. But look at these two, cube root, accounts now delinquent, and total collection amount. We're still not even close to fixing those with the cube root either. So I forgot that we're only going to see so many columns here. I wonder if we even got it here with the natural log. I might have to remove some of those earlier pills just so that we can get out that far. Yep, so let's do this. I'm going to stop this one, and I'm going to get rid of our cubed root option here now that we've learned what that one looks like. And in fact, on this square root one, I'm going to do this. Well, I can't do it in place, can I? Just to keep things simple, though, on this pill, I'm going to do in place. So I'll adjust the originals just for argument's sake so that you can see it. All right, let's run that. All right, well, that's still running. Let's take a look here at our natural log. So here, because I did it in place, I want you to see how this works. These numbers right here are already adjusted to natural logs. So notice before the loan amounts were pretty high. Now these numbers are pretty small because of this. And now, in fact, we've overcorrected it, and loan amounts got a negative skew here with the left tail. Those ones weren't really that skewed in the first place, so that's why that happened. Interest rate and installment, however, those were very right skewed, and now they're looking much more normal. Maybe a little negative skewed on installment. Let's go over, though, to account here, these accounts now delinquent. Now, look at this. Total current balance, the kurtosis is a little bad, it's high, but the skewness, it's pretty balanced. I think we've corrected that one entirely. Total collection amount, before, even with a cube root, only had 1 bar. Now we've pulled at least a few outliers out of it and moved them over here. And revolving high limits, a little better than it used to be, although we never fixed account now delinquent. So what do I do about this? Really, these two. where they're so right skewed that even a natural log won't fix them. Well, here's our values here. What I would do on these, where you have so many values that are 0 and so few that are not 0, I would turn both of them into binary or Boolean features, and I would change the actual balances to 1s. So if they have any balance at all, or if they have any number there, or collection amount or counts delinquent, give them a 1, otherwise leave it as a 0. And there's different properties with a binary feature like that from a continuous numeric feature like these, and that would be a good way to handle that. All right, so that's how we fix positive skew. I'm not going to go into negative skew. I'm simply going to show you that if you do have negative skew, you can just do the reverse. Instead of a square root, do a square. Square the term. Cubed root, do a cubed term. And the inverse of a natural log is exponent. Take e raised to the x. Now, just in case you're curious where that is, I still go, I believe it's here in the basic category. And there we go, right here. I believe that's it at least. Yes. If you want to use a power different from squared or cubed, you can use this power, and you can raise it to the 4th, 5th, 6th, whatever you want, and all that. So that's how we apply a math operation in order to correct skewness.